Hi, all. It gives me great pleasure to welcome Dr. J.P. Bardet, who is professor in civil and architectural engineering at the University of Miami. He's going to talk about the resilience of urban water infrastructures, which is going to address pipe failures. So a little similar to what we were just talking about a second ago. Dr. Bardet served as Vice Provost for Strategic Projects and Dean of the College of Engineering. Before joining he was Dean of the College of Engineering at the University of Texas at Arlington. He started his academic career at the University of Southern California, rising through the ranks of USC to professor and chair of the Sunny Astani Department of Civil and Environmental Engineering. At USC, he was also director of the USC Center on Megacities. His research interests are very broad. They include higher education, infrastructure systems, geomechanics, geotechnical engineering, and multi-hazard engineering. Thank you very much again, Dr. Bardet, for taking the time to do this talk, and we are eager to hear from you.
Thank you very much, Prano. Indeed, it's a pleasure to talk to you, not as an administrator, but as a researcher. Today, I'd like to cover a topic which is, I think, very important, which is the resilience of urban water infrastructures. I'm going to give you a case study, and that explains the subtitle of the presentation, a case study from Los Angeles, where I spent 30 years. And I will explain also the feature of this case study by using a model which has been published in the Journal of Water Resources. So I'm going to take you on a journey into water, and especially in California. Now, I must say that I have to acknowledge a lot of people. The result you're going to see today are actually the results which came out of a team that I led. It includes people from the Los Angeles Department of Water, quite a lot. A company, private companies, JPL, the Jet Propulsion Laboratory, which was instrumental in giving us remote sensing data. And many others which are listed here, including universities. We had Caltech involved, California Institute of Technology, and RPI, and Cornell University. So this was a joint effort, and I was, fortunate to lead that team. Now, let me tell you exactly the problem now. I'm trying to define the problem, and then we will go through the analysis. Now, if you look at the report card on infrastructures from ASC, the American Society of Civil Engineers, you can see that overall, we are making progress, but we still can make more progress. You can see the report card in 2009. Overall, we got a D. And now we are getting a C-. So we're still not really passing. We still have bad grades. And you're talking about 12 years of progress. So, but if we concentrate on water, what is really relevant to water? That means the dams, the drinking water, the wastewater, and the levees. You can see we're not doing too well. And just for putting in perspective, I mean, that's a quote about the fragility of our water infrastructures. There is a water main break every 2 minutes. So as I speak, we're going to have 30 breaks in the nations during my talk, which is going to last hopefully just 1 hour. So in 2021, again, this is a detail of my previous slide. You can see the dams are getting a D, drinking water getting a C-, the levees are getting a D, and the stormwater are getting a D. So not well, okay? Just below the average C-. Now in Florida, we're getting a C. So we're doing better than the nation, okay? In dams, we're getting a D-, and we're getting a D+ for the levees. Now, that is certainly going to come to light as we discuss Hurricane Ian. The stormwater, we're getting a C-, and the drinking water, we're getting a C. in my opinion, I'd like to know more about why we are so optimistic. And just to gain some facts to understand that we're dealing with a huge water infrastructure system of the nation. We have 2.2 million miles of underground pipes to distribute water. Just in perspective, the distance from the moon to the earth is only 239,000 miles. So basically we have 10 times the distance moon-earth in our water distribution infrastructures. We can see that we are leaking quite a lot of water. So each day we lose 6 billion gallons of water through leaks, or some obvious leaks that we can see, some of them being quiet and not seen until actually they manifest themselves by failures. So I just did a research just before the talk, just to see what's happening today. And you Google, and guess what? You find a lot of breaks all over the United States. New Jersey, we have one in Albuquerque, one in Hawaii, on Hawaii. So you can see this is going on and going on and going on. And these are massive, I mean, they're very destructive, such as, for instance, here, one of them affect 93,000 people as we speak. Okay, when I was just doing some more research before to prepare this talk a little bit to document it with recent news, here are some pictures coming on August 16 this year, and you can see the typical picture. We're going to see over and over flooded streets, failure of pavements, geysers, which are kind of spurting out of the ground. Okay, these are the typical picture of failure of our water infrastructures. Florida, we don't escape the problems, and there are some pictures out of the internet. You can see the typical sinkhole, which are formed by when we have a water pipe, basically, which is leaking for a long time, and basically erode the soil around it. And later on, when we have a driver, which unfortunately drive on top of it, we have a failure like the one on the picture. Okay. Now, I'm going to take you back in 2009, the case study, which I have documented in great deal with the Department of Water and Power, showing you that the news were really aggressively reporting these failures. It was a real disaster in Los Angeles. News, radio, newspapers, everybody was worried. The city was like under attack. Okay, and you can see some of the pictures here and clippings of the papers. This is a kind of failure we've seen. Geysers shooting water in the sky, and obviously this was attributed to a failure of water mains. A truck, and it was a very advertised photographs of a truck which basically sunk into the ground because the pavement has been basically undermined by a huge leak, and the leak had carried out the soil. Therefore, there was a very fragile pavement, and the result was what you could see. And there are some more pictures, typical pictures of failures of pipes and their consequences coming out of LA in 2009. Now I'm going to define some brief quantities just to give you some references. We're going to use the word blowout when we have a surface disruption of the pavement, which is about 100 square feet. So that gives you, just to give you this an evaluation of the size of the events. So 100 square feet correspond to a blowout. And so the rest, we're going to call it leaks. Okay. So this graph shows you, it's a cumulative graph over a period of 10 years almost, showing you how the blowouts, how many blowouts we have each year in Los Angeles. 205 per year. Okay, that's quite a lot of blowouts. Of course, it's much less than the number of breaks per year, which goes about to 1,700 per year. Now, this, this is obviously what is really striking when I saw that graph is how linear this these phenomena are. There is something here which is puzzling. How are they are so linear? Okay. Another way to show the graph is looking at the number of blowouts that during the summers. So summers in Los Angeles are particular seasons where the water obviously is in greater demand. And you can see that in 2004 it was 80 blowout during the summer. Remember 205 during the full year. And then it was a decrease. So there was like this, I think we are taking things under control. And then in 2009, 101, we doubled basically what we had seen the previous summer. So that was really a point of concern, okay? And you can see the ratio shows the ratio between the leaks and the blowout also shows the same feature, a sudden increase in summer of 2009. Okay, now let's step back and talk about the Los Angeles Water and Power, which basically is the entity, the agency responsible for distributing water in Los Angeles, founded in 1902. Now, LA would not exist without this entity. And yeah, movies actually, which you can see, old movies about how the studios actually depended on the water in Los Angeles and how there was all kind of actions against the water, the development of water in Los Angeles and so on. Watch these old movies, are very interesting. But we serve, LADWP serve 4 million people, okay? And average at the time, 2009, was about 144 gallons per person, right? And they have about more than 7,200 miles of pipes in the ground. That means that's a distance between New York and Paris round trip, okay? The system is can be broken down in many pressure zones. Now, LA is made of mountains and plains and between them. So there are combinations of pressure generated by pumps and just gravity pressure using the mountains to store the water in reservoirs. So a very complicated system and not really, I would say, complex. So you can see a corridor leading to the port of, if I may get my, getting to the port of Los Angeles at the bottom, okay, at the southern part, but very complicated structure. All right. So we need pipes, and here is a 3D graph showing you the makeup of pipes, different materials, and you can see quite a lot of materials. This graph only shows you the main materials, which are cast iron, CI, steel, ductile iron, asbestos concrete or cement pipe, and which were put in the 1930s. And you can see the major type of pipes are cast iron, okay? You have also in the third dimension, you can see the diameter of the pipes. Okay, that's another picture showing basically the distributions of pipe by length and that the major composition basically of the water infrastructure system is cast iron. Okay. All right. The age. Now, yes, age. We're talking about aging infrastructure. So here is a distribution of the age of the pipe when they were installed in the ground. And you can see we have pipes which are above 100 years. Okay. The majority of pipes would be, the peak would be around 60 years old. Okay. So we can say an aging infrastructure indeed. Now let's see how things fail and breaks. Now, we have an association called the American Water Work Association, which reports statistics, and there's about 25 breaks per 100 miles per year in the nation. Okay. What they reported is the cast iron is really the culprit of these failures. Cast iron has been extensively used to build water infrastructure systems, right? And the utilities company basically replace their pipes just when they break. That's the simplest way to proceed. Instead of replacing good pipes, they wait for them to break. That was the practice 10 years ago. Some of it has changed over time. All right. So we can say that indeed the replacement is very slow. In my first slide, we have seen some statistics. They are replacing, yes, everywhere in the nation, pipes are being replaced, but are they being replaced fast enough to prevent these kind of failures? Obviously, you can make up your mind after this presentation. Now, the factors contributing to failure are numerous. We have to look at two aspects: the demand, which is basically what we ask the pipe to respond to, and then their capacity, their ability to resist to demand. Okay, there are many sources of demands, as you can see: water hammers, changing in water use, temperature, traffic loads, subsidence, and so on and so on. Soil corrosivity. We're going to look at some of them, and obviously the capacity. What are the factors which affect capacity, okay, are listed here too. I'm going to isolate some of the principal factors in this study. All right, let's see how things fail. You see some kind of pipes, cast iron pipe failures here. You can see a circumferential failure, kind of a beam break. You can see a longitudinal failure. And sometimes you can see a chunk of pipe, which basically explode from the pipe due to some kind of weakening of the pipe. We have old pipes, pipes which are made of steel, riveted steel. That's an old type of constructions. And you can see they also break, but they break in a different way. That's steel, that is not cast iron. All right, so the typical failure we see, and if I summarize, the longitudinal failure, the pieces which are blown out, and the circular breaks. So these kind of failure are usually very, energetic, and especially when a piece is blown out, correspond to blown out. Okay, some other pictures, you can see really that the internal stress really is responsible for the propagation of this longitudinal crack into the cast iron, and showing really that we can see the initiation and the crack propagating on both sides. Okay, that's another view of similar pipes. Actually, Los Angeles, the LADWP has a very nice collections of broken pipes, and they do some very nice metallurgical analysis, trying to understand why these cracks initiated and trying to understand how they propagated. Okay, all right, so you can see these kind of pictures which shows the surface of the cracks. And also all kind of metallurgical analysis showing the cast iron. The cast iron is full of impurity, and this impurity are going to actually create the nucleations of those cracks, and which were responsible for what you have seen. Ductile iron is completely different. Ductile doesn't behave like brittle like the cast iron. It's just much more homogeneous, and we have this ductility which doesn't correspond to crack propagation. Okay. Another phenomenon which is important is the corrosion. Cast iron graphitized. In other words, the cast iron gets back to graphite. And we have a weakening, usually created by corrosion, and a thickening of the wall of the pipes, which are the natural place for stress to concentrate and where the cracks to initiate. Now let's do some statistical analysis since we have such a huge system. Okay, well, most of the data we're going to get is from the data that we gather when we fix leaks. And you can see me actually with one of the crew here fixing leaks. I was not fixing, I was just measuring. a device which basically is a listening device to tell us if we can hear the whistling of the water hissing when it leaks inside the ground. That's before we start digging and expose the pipe. Okay, all kind of techniques to fix leaks, and you can see here kind of a belt that you wrap around the pipe, and that's some of the workers fixing the pipe. Now, the data is critical for any engineering investigation. And here we discovered that data is not always well collected. But let's kind of walk you through the process, how data is really collected. Well, first it starts usually with a phone call. Oh, my street is flooded, come and help me. So there is a report filled into the water trouble system. Then, of course, the crew has to identify the location of where the pipe is actually leaking. Now, you think you would have a GIS system which will tell you exactly where the pipe is located. Well, no, look, they use basically the good old Thomas guide, which is one of the maps that you use in LA to navigate. Or you can use a Yahoo report at Google. So you locate basically the place, okay, based on the phone call you received. And then the most data is coming from the repair, the crew. You have to bill, obviously, charge, pay salaries. And so there is a lot of information taken at this level, which may or may not make it into the data collection systems, such as the construction productivity tool or the GIS, because now many water utilities have GIS systems, okay, to collect data and to analyze their systems, okay? So, but look at the statistics. There is a huge loss of data when we talk about the leak report and actually how much data makes it to the GIS. There is a substantial difference. Things are getting better now. We collect more data, but still a lot of data is being wiped out. Okay, let's look at some results. Now you can see the various period of time, number of leaks, as we said, about 1,700 per year. You can see the blowouts a little bit vary on average. We said 205 per year. And you can see the ratio of blowouts to leak. So there is obviously more leaks than there are blowouts. Okay, and now let's look at the materials and the leaks and the blowouts. The blue is a cast iron, and we plotted in two different ways. One not normalized, the other one is normalized. And you can see the system, how important is the cast iron in the leaks and the blowout. But obviously, it's kind of expected because we have a lot more cast iron in the system than the other materials. But if you look at the blowout, what's really striking is that most blowouts are in the cast iron, the blue, over the year. Okay, the diameter of the pipes doesn't make that, is not that significant in the failure, in the leaks or in the blowouts. Now, LA, is this really a special city? No, it's not. But let's look at other cities, and I have to wipe out the names because I don't want to point fingers at anyone. We see that LA is quite substantial, as with 7,200 miles of pipes. Another city, City Z, has 8,000. Maybe you can guess what city it is. But so the cities have a lot still of cast iron. You see the blue? That's still a lot of cast iron in all our cities. Okay, and show you the distributions, a bit the 3D distribution. Again, a lot of cast iron, and we see the same material, steel, ductile iron, and asbestos concrete. And there's the failures. And so they are reported as number of breaks per 100 miles of pipes. And see, the magic average is 25 breaks or leaks per 100 miles of pipe per year. Okay, LA is the blue. So LA is actually not doing too bad. There are other cities doing very poorly, and some others doing better, as you would expect. Okay, now let's zoom on the driving factors. Corrosion, we've seen a picture of what corrosion can do to cast iron. And obviously, when you're looking at a large area like Los Angeles, you have a lot of different corrosivity, soil corrosivity. The red indicates very corrosive and the light yellow, less corrosive. A lot of variation of corrosivity throughout the system of Los Angeles. There are plotted here some histogram based on this spatial analysis. You can see we have all kind of, we measure corrosivity by measuring the resistivity. It's obvious corrosion is the result of some kind of transfer of electron, okay, or ions and cations. So the resistivity is an important measure to identify corrosivity. And so we have graphs to measure, to report the relationship between corrosivity and breaks or leaks. And you can see as the conductivity increase, which is the inverse of resistivity, you can see obviously that the breaks or the blowouts increase. And now if you factor the age, the duration of the exposure of the pipe to this corrosive environment, you can see at the bottom a very nice steady increase with this conductivity multiplied by the age. Temperature. Okay. Well, temperature is thought to be a factor in many parts of the United States. Why? Because we have freezing grounds, and soil in freezing grounds obviously are going to be somewhat subjected to thermal stresses. Well, in LA, the water temperature doesn't change very much, and the ground, LA benefits of a great weather all year long. So there's not much variation of temperature on the ground surface. So there are some, but not very significant compared to up north in New York, Chicago, and other places like that. Okay, pressure. Well, if temperature obviously doesn't vary that much in the water, obviously temperature affect people who demand water to water the lawns or maybe just for irrigation purposes. So water pressure, we measured with Caltech, a company which is run by, I think by a former professor at Caltech. We measured the water pressure at many different locations. And you can see this kind of fluctuation over time. That's a monthly scale, different locations. And you can see an average curve, but you can see also ups, downs, constant, almost water pressure drops in the water system. Okay, and especially in June 1st, 2009, LA embarked on a very ambitious water conservation program to cut basically the water going to irrigation of lawns. They did, and they implemented 2 days watering per week, only Mondays, only on Thursdays. Okay, so that was on just a few months after our investigation, before our investigation. And you can see in the graph here that the water pressure in PSI, okay, varies on Mondays, and on Thursdays, you got the low pressure, and the pressure goes up during the other days on average. So everybody was watering their lawn on Monday and on Thursday. Pressure in the system was dropping down, expected. Okay, we did also some more measurements, some fine measurements now of transient. Transient could be responsible to water breaks. And so there were like a lot of different measurements, very precise, which I'm going to show you, where we basically put sensors in the systems, very sensitive sensors to measure the water pressures. And these are locations of these sensors. And you can see how fine of measurements we were getting, but still we were getting some very nice fluctuation, the daily fluctuations, okay, of the water pressures. We were also able to measure the breaks of other pipes. So when there is a failure within the systems, the water pressure certainly changed, affected locally, and we can measure a few miles away actually the water pressure. We can even do triangulations. Well, it's complicated because it's not Euclidean, but we can triangulate and find what is the source, where is the source actually of the break. All right, so this is basically this kind of showing the variation of the pressure caused by pumps when they start, closes, and so on. Okay, so very fine measurements. Now, our main finding, and I summarize them in the case study, we had a lot of pipes, 7,200 miles. Most pipes were made of cast iron. We had a very, very concentrated failures in 2009, the summer. Okay, suddenly things get out of hand. We got 101 blowouts in one summer when we had only 50 the previous summer. We noticed that all failures were the massive failure were in cast iron. We found that Los Angeles was not doing worse than the other utilities or the cities. And we found that there were relations between temperature and obviously an internal pressure. And we pointed the finger at this water rationing program. Good intention, but with unanticipated consequences. Suddenly, everybody was drawing from the systems on Mondays and Thursdays, and guess what? This unexpected stress induced by this synchronized pumping basically created metal fatigues, which I will cover in a minute, and basically created failures, a resurgence of failures. Okay, we gave our recommendation to the City Hall. I was chairing the Blue Ribbon panel, and we basically gave them a solution, and we asked them, instead of just drawing water on 2 days, why don't they use the odd and even side of the streets to spread the water pumping over 4 days instead of 2 days? Guess what? It worked, and the blowout stopped. Okay, we asked them also to put more money into research. Some of it, as they listened, some of them listened, but not completely. All right, I'm going to pass on that. Now, one message I want to send to the listeners is I talked about the science. I talked about the engineering aspect. And you can see here a timeline where I'm going to trying to show you the evolution of the project. From the inception, when we basically witnessed the failures, we basically had meetings. The Center on Megacities, which I was directing, basically was involved. We were asked to come and give some advice. We had a contract from the city. We met with LADWP, defined scope of work, then started our research. Okay, so there was a phase. How many months? Well, maybe 2 or 3 months of work, hard work, but intense. But that was engineering, basically trying to discover what was the source of the problems LA was experiencing. But one thing, after our findings were basically released, right? They were released, the news were on us, radio and so on. It was a very intense moment. We had to convince people that our findings were okay. To this day, I still have people who don't believe that we found the right problem, although our finding produced results. There is a lot of people to convince when you talk to a city. First, you have to make sure the agency is on board. But I was lucky, there were some great directors at the time, and they were very listening. But we had to go to the city council, make presentations to different levels, small committee, larger committee, the big city council, and explain what happened and how we could solve the problem. So before we got to August 25th, where the city agreed to change the water rationing program and to decrease the demands on the water distribution system, is there are a few months of basically explaining, repeating, and basically PR, just to make sure that we were correctly understood. Okay, so that's something I'm proud of, because finally we were able to do something which affected something good, which affected 4 million people, all the Angelinos people living in Los Angeles. Now, let's talk about some more science, which came out of this research. And I want to present a model, the harvesting model. I was fortunate to have in the team Richard Little, who was an expert in infrastructures and had worked with the National Research Council. And so we were obviously looking at this kind of failures of an aging system. We had to look at it from a different perspective. If we go back to our books in engineering, usually we design a system for a certain demand. So we make sure that the capacity of the system is larger than the demand. Okay, so the system doesn't fail. But what happened when the capacity of the system start to decrease? And so how does the system really respond when we have this decreasing capacity? And especially we were intrigued by why we have a surge of failure, why suddenly everything will start failing at a given point. Why? Okay, so that was really the question which prompted this model, the harvesting model. And we were inspired by like Isaac Newton almost, the harvest. If you have an orchard with apple trees, when the apples get ripe, it won't take much of the wind for the apples to fall. So as I said, as apple, eventually, all apples are going to fall, eventually, all of them. But the riper they are, the more will fall when there is wind. Okay, that's very easy to understand. Now the same concept was applied in epidemiology. Our colleagues in public health came up with models for mortality rate after heat waves. Here's some graphs showing that if you have, that's the bar here, will indicate the mortality rate, and here the temperature. If you have a sudden increase of temperature, and you get it's Celsius, so 30 degrees, 35, start to be pretty high. You see some increase in mortality. Okay, that's been published in journals, and they developed a model called the harvesting model, a model based on the same concept as the apples falling from the tree. Some examples here, in particular, giving us more details within the model, coming from Zeger, showing that as you look at your makeup of your populations, the mortality strike mainly the older populations. Well, I think there is a strong parallel with water infrastructure. Okay, and we have a lot of data from epidemiology showing various parts of the world that this part of the world experience similar problem, sudden surges of mortality in populations of older populations due to heat waves. Okay, so here we're going to take this analogy and trying to push it and adapt it to infrastructure systems. You can see LA, you can see the distribution of pipe age. Okay, now age is not a determining factor by itself. It's more the degradation of the pipe, which would be a better measure. But age is going to be related. Okay, of course, in the makeup, the material making the pipe. And LA has this very vast system of pipe. It's confidential. I cannot release the exact position of the pipes. But this picture is so basically so, I would say, hard to see, you would say. You can see all the little red would be pipes. So a lot of pipes. So we have a good statistical basis to analyze, to make a model, statistical model. Okay, show you this picture of the blowouts and the other leaks, and compared to the mortality rates, which I've showed you before. There's a similarity. We see sudden spikes in breaks, in leaks, or in blowout. Okay, all right. So what goes in, and why do they concentrate? Okay. This is another picture showing it's maybe it's not as fine, it's more concentrated, but showing the variations of blowout and leaks in Los Angeles, something I showed you. Again, I stress this important graph, which when you plot the cumulative, it seemed to be a very significant linear trend in the blowouts per year. I was amazed that when there's a constant ramp here, constant slope almost, okay? And another thing is temperature, either the minima or the maxima seems to be related to the blowout. You can see the two pictures showing blowouts and the mean and max of temperature. And the dark circle show you the blowout during the summer, and the empty circle, the blowout during the winter. And the max and the mean of temperature are shown here. They seem like each time you have an extreme amount of temperature, you have a max of blowout. So temperature is obviously related, but not directly. It's related through the demand of the population and through the basically the change in pressure. So the model, the harvesting framework, as we start formulating it mathematically, introduce a concept of what is called a frail population. You have a general population, and you introduce this concept of frail population, which is about to fail, which basically is about to die, or it's about to blow up. But it's this bucket which comes from many factors, and then the general population fill that bucket of frail population. That's going to be a very important concept, because if the bucket is full, then you can have a lot of failures. If the bucket is empty, you're not going to have that many failures. Okay, so this is a very critical concept in the model, which breaks from other models where you define what we call frail population. If you want to plot it in terms of statistical distribution, you can actually plot here the strength at different times. So there will be the third dimension will be the time. And you define at the bottom of your weakest population what we call the frail population. Okay? And so there is obviously a part of the population which has already, the population of pipe which has failed, and there is the one which are close to failing. Now, if you create a stressor on the system, what do? You basically shift the distribution, and you you dip into the frail population. Okay, so you basically draw from that reservoir of frail pipes, and you fail them. Okay, and here again, this graphic that you have seen, showing you that we have all the ingredients here to create this model. Now, where are we going to define the frail population? How are we going to define that? Well, that's why comes the concept of fatigue, metal fatigue. I'm going to show you, if I can, a movie. It's not a high quality movie like you can find in Hollywood. It was done with a very low budget, but it illustrates metal fatigue. So, and it's done some years ago. I did it to explain to the city hall what we were dealing with. So we used paper clips, paper clips like in your drawers, and we basically bend them with small amplitude, about 90-degree amplitude here. And we're going to count how many cycles to fail that paper clip. You can repeat that in real time if you want. 12 cycles you can recount. Now we're going to do the same thing again, but now with a larger amplitude, okay? Almost 180 degrees. One more, and bingo, 4. So we went from 4 to 12, 12 to 4. So here is metal fatigue defined. If you increase the amplitude of cycle, you are going to get less cycle to failure. Okay? Very simple. Okay? And I was inspired to do that. It was just after the failure of the one of our major rockets, and one of my Professor Cal said actually explained the failure from this little O-ring by dipping into liquid nitrogen and breaking it like that. And I was told, if you can do something similar to that, you're going to convince the city hall that you got the right solution. So I'm going to go next step. Okay. So in graphs, a metal fatigue is basically you can plot the number of cycles versus the peak stress, the stress that you induce. But it was obviously at the point where I was twisting the paperclip. And we were obviously had to make sure that this data comes from the laboratory on cast iron, I think from Canada. And we basically we assessed the stress in the wall of the pipe, and the lines were pretty close to the fatigue limit. Okay? And suddenly when we are this showing you how the crack lengths really increase when we are close to the failure. Okay. All right, so back to the model. So now, instead of using strength, I am going to use the number of cycles to reach failure. Number of cycles to reach failure. So if I have a sudden increase in stress amplitude, that means I'm going to have less cycle to failure. Okay, that's a concept. So and now I've given a concrete realization of how I define frail. Frail pipes is when you are close to the maximum number of cycle. Okay, but what's important is that since number of cycles depend on the amplitude of your cycle. Okay, so we're going to spare the mathematics. It's pretty simple mathematics, which basically give you the cumulative number of breaks, the break rate, and give you also the variation of the number of cycles which come from the demand on the system. And we're going to look at very simple stressors, okay? And we're going to show some features which I think are unique. Dirac function, a sudden stressor at a given time T0. So suddenly we're going to reduce the number of, because we have an increase in the cycle amplitude, the number of cycle to failure. Okay, so delta N is negative. And if we look at the, we're going to keep assuming that if we don't have stressors, we have this constant slope. And then we have an impulse, suddenly we break. And guess what? After that, since we depleted the bucket of frail pipe, we have no failure. So the break rate is 0. So we go from the break rate, which is somewhat constant, at B, we call it B value. And then when we have the impulse, we jump, and then we go down to 0. And then we have this period of quiet. We empty basically the chamber of frail pipe. Math is described to the right. Now, let's put two impulses next to each other. we are going to have the factor, we're going to have what we call shadowing. The first Dirac, the first impulse, will break most of the pipe, or all of them, depending on the amplitude. And then the next one will have fewer pipe to work on because it's the weak, the frail population has not been repleted, has not been renewed. So the second impulse, although the same amplitude, will trigger a little bit an increase in cumulative number of pipe break. Amazing. This is a fundamental feature of the model. Now we looked at different impulses such as triangular pulse. Instead of using a Dirac, which is rather radical, simple pulse. And we see in the cumulative number of breaks, we see these nice shapes. So that would be the break rate, and this is the integral of the break rate, okay? And they don't have to have the same slope, okay? And we see this nice feature, kind of a bump, a smooth bump, all right, instead of a Dirac. But you can see that the rate here is somewhat smaller, okay? So what's happening? In fact, it's like you have a frail population coming into a room, and you have here a chopper. Suddenly, if you increase the demand, a lot of people go into the room, they're gone, okay? And my chopper still operates here. There's a gap in the frail population. There's nothing happening, or very little happening. And here it shows that in this rate is actually steeper. We're going to see the flat curve, which appear again, like we have seen in the Dirac. And now we have a tool. We can look at all the failures in the systems and identify some stresses striking at different times of different durations. And you can see here an hypothesis. Now, this is a non-unique solution. The stressors, remember, are shadowing others. So we are only picking up the stressors which are the most significant. And we can derive some pretty nice simulations for what's happening in the system, including the sudden increase in breaks. And now the stressor plotted like we plot them in seismology, showing the various impulses at different times. And I'm sure we can simplify that in the future. I'm working on some new models now. Another stressor, which is a little bit more sophisticated, is a cosine, half cosine or cosine stressor, which gives us a smoother curve. Okay, and same principle as the bilinear stressor. And here we can model, the observations and identify the stress of the end system. Okay, so what are the consequences, the practicality for utilities? Well, we have a new model to explain why things suddenly increase suddenly. So there are good news and bad news. Bad news, you better, you're going to expect, if you have a quiet period of no failure or little failure on your system, okay, and you know that your system is pretty much a constant rate of failure. Well, guess what? If you have a stressor which is a little bit bigger than the others, you're going to have massive failure in your system. Now, the good news, if you have a major event happening, okay, like an earthquake or a hurricane, and you have a lot of failures, then after this surge of failure, you're going to have a quiet period. So you're not going to have failure after a massive failure because you have depleted the frail population. Okay, so I'm going to conclude. I don't know how much time I'm left, just on time. So we are aging water distribution systems, and they are getting more and more vulnerable. This is, we don't know. This is clear. Okay. They may fail in temporal clusters, and we've seen that frequently, sudden surges of failure. And we see the same thing in human populations, when we have heat waves. So there's an analogy. Okay, so we have a new model. It gives us a new insight into how aging water infrastructures fail. The system also applies to many other infrastructure systems, I hope. Okay, so again, it will predict the period of surges of failure and the period of quiet, almost no failure. And there's much more study to be done to explore the model and its applicability. So I'm going to wrap it up here. This is my conclusion. Thank you very much for your attention today. Thank you.